Today we're going to be talking some more about the work energy theorem, which is what we were looking at yesterday. And when I say we're taking notes, it's not so much notes as more example problems. Some of you feel really comfortable with it, at least that's what y'all told me yesterday. And some of you feel like you could definitely use some more practice and you're still having trouble with it, and that's okay too. But because of that, I wanted to go over it some more and, again, take out some paper so that you can work through them with me when we go over the notes after today's warm-up. After we go through the notes today as well, you do have an assignment, 902.3, Work Energy Theorem Problem Set. The assignment due date is tomorrow. I did not put the due date for today. However, tomorrow we will be doing an RA, and so you will not have class time to work on that assignment. So although it's due tomorrow, that just really means that I'm giving you more time to work on it outside of school if necessary. Hopefully you can finish it today, you have class time today, and if so, you'll be good. You won't have to worry about finishing it up for homework tomorrow. But in the event that you haven't finished it by the end of the period, you can work on it tonight at home or even tomorrow at home. Let's go ahead and go over the warm-up question and get into those notes today. And again, guys, please take out some paper so that you can copy down some of these examples. The warm-up question says, a ball sits atop a frictionless ramp before rolling down the incline from point 1 to point 4. Where is the total mechanical energy greatest? And then question 2, where is the kinetic energy greatest? And then question 3, where is the gravitational potential energy greatest? So let's start with the first question. We have 4 labeled points, 1, 2, 3, 4. Which of these points would you say has the greatest mechanical energy? I just heard a couple of you say it. They're all equal. Okay, and so your mechanical energy should be the same at all of those points because there is no external force acting on that system. We have that ball sliding down that ramp, but there's no friction acting against it. There's also nobody pushing it. Okay, if we think of the ball-earth system, there are no external forces acting on that object. And so we would have the same amount of total energy. That's the law of conservation of energy. Now the forms change because we have more than one form of energy here, but the total mechanical energy, which is the sum of the kinetic and potential energies, remains constant. Okay, but that brings us to number 2. Where would we have the greatest kinetic energy? 1, 2, 3, or 4? Yeah, 4. That question, what I'm really asking you is where is this moving fastest? Okay, and it should be at the bottom of the ramp, which is at point 4. And then the last question, where do we have the greatest gravitational potential energy? 1, 2, 3, or 4? Katie, what do you think? Where do we have the greatest gravitational potential energy? At 1. All I'm asking you in that question basically is, hey, where is this the greatest height? Okay, so you should be able to answer those questions. And if you haven't done so already, please make sure that you are answering them in My Open Math so that you get credit for the warm-up questions today. All right, follow-up question to today's warm-up. Okay, let's put some numbers to it. It says a 1.5 kilogram ball is released from rest atop a 3-meter ramp. If the ball is moving 6.5 meters per second at the bottom, is there friction on the ramp? Guys, you should be able to do this question. We've done some like it yesterday. We did some like it in the work energy theorem unit. Okay, work kinetic energy unit in December. Okay, so we're coming back to it. But in this question, I'm telling you some information about this ball at the top, so like at point 1, and then at the bottom, like at point 4. And we already know that this ball starts at rest, and so it has gravitational potential energy at the top. Y'all told me in the warm-up that's where it has the most. And then at the bottom of the ramp, it has kinetic energy, and it no longer has height. And so we couldn't figure out, does the gravitational potential energy at the top equal the kinetic energy at the bottom, or are they not equal because there's something doing work to remove energy from that system? Is there friction? So that's what we're going to do. We're going to figure out how much total energy we have at the top and how much total energy we have at the bottom. Is the GPE at the top equal to the KE at the bottom? So let's solve for gravitational potential energy at the top of the ramp. It's just mgh. We know the mass, it's 1.5. We know gravity, it's 9.8. And we know the height is 3. So if we want to solve for that gravitational potential energy and we multiply those, we get 44.1 joules. The question is, do we still have 44.1 joules of energy at the bottom? And they gave us a velocity. We still have the same mass, so we can figure out how much energy we have at the bottom. Ke equals 1/2 mv squared. That's 1/2 times 1.5 times 6.5 squared, which gives us 31.6875 joules. Those are not the same. Okay, so to answer that question, is my mechanical energy conserved? No. I lost some. Or to answer the question we're being asked, is there friction on the ramp? Yes, there is. Okay, because there has to be some external force causing my energy to be lost. And then I could ask you a follow-up question, how much energy is lost? How much energy is dissipated due to friction? And all you have to do now is subtract those two numbers. I know how much I started with, I know how much I have now. What's the difference between the two? Okay, and so we could do that. 44.1 minus 31.6875 tells me that I lost 12.4125 joules of energy. That would be my energy dissipated due to friction. Now, one of the other ways that we ask pretty much the same question is, what is the work done by friction? And if I asked that instead, you would need to put a negative sign in front of it, but it would otherwise be exactly the same answer. It's the same magnitude. It's just that the work is negative because that's the energy that's removed. Okay, does anybody have a question about this example? Y'all are going to have to do some today, so it would be a good time to ask if you're not sure. All right, so I wanted to do an example today that included elastic potential energy because we haven't dealt with it in most of our examples. It's just been KE and GPE. So I have a bungee jumper. Okay, and it says, if a 63 kilogram bungee jumper causes a bungee cord with a spring constant K of 88 newtons per meter to stretch a max distance of 28.4 meters from its resting length, from what height did the bungee jumper leap? Okay, and so they're asking me questions about this bungee jumper, but they're giving me information about the elastic potential energy that the cord has when it's fully stretched. They're not giving me information about his height or gravitational potential energy. So I need to write my energy transfer equation because if they give me EPE, I can probably set it equal to something. So again, I'm going to remind you of the steps that we've been using to solve these calculations. We start with that energy transfer equation, and sometimes it helps to list the given information first and look and say, oh look, they gave me a spring constant and they gave me an amount of displacement of the spring, or the bungee cord in this case. Okay, they must be giving me information for elastic potential energy, or hey, I have a mass and a velocity. Look at the givens. It will probably help you figure out what energy forms are present. If they give you a velocity, you've got KE. If they give you a height, you've got GPE. If they give you a spring constant, you have EPE. Okay, so look at the given information, use it to help you write that energy transfer equation. And then usually you don't need the energy forms, you need the masses and the heights and the velocities and the displacements, and you need those other variables. So substitute those in so that you can then plug in your numbers and solve. Okay, so let's go ahead and go back to this question. And they gave us information about this point where it's fully stretched at point 2, but they asked us about the height that he leapt from at point 1. So we're going to write an energy transfer equation that shows the energy change that happens from point 1 to point 2. And that's what it says. Write the energy transformation equation for the bungee jumper from point 1 to point 2. Assume the height at point 2 is 0 meters and that there is no friction. Okay, so with that said, energy form at point 1. When he's just standing up there, so Austin, when he's on top of that platform at point 1, what energy form does he have? GPE, gravitational potential energy. He's not yet moving. Nothing has been stretched. The bungee cord is not stretched yet. It's just gravitational potential energy at point 1. At point 2, he's down here, and you can see it when he falls. It's the point before he springs back up to 3. Okay, what's happening at point 2? What forms of energy do we have there? Is he moving at point 2 when the cord is fully stretched? No. He actually stops before he gets flung back up. Now he's moving in between 1 and 2. He's moving in between 2 and 3. But at point 2, he actually stops for a split second as he has fully stretched the cord before it flings him back up again. So no KE because he's not moving. And the question tells me to assume that the height there is 0. So no GPE. So what do I have there? Elastic. Yeah, elastic potential energy. He has stretched the bungee cord. So that's our equation. The GPE at point 1 equals the EPE at point 2. Again, guys, if you can write that equation, that's half your job. Okay, that really, if you can't get there, you're not going to get the right answer. You have to be able to do that step. Okay, now, again, if I go back to the question, they didn't give me energies. They gave me mass. They gave me a spring constant. They gave me a displacement. We want the variables. GPE is mgh. EPE is 1/2 kx squared. That's what we substitute into. So let's bring that equation back to the question. Okay, so now we can put the numbers in. Same question we were looking at a second ago. Putting in the numbers, we have his mass is 63, gravity is 9.8 times height equals 1/2 times k is 88 times 28.4 squared. Okay, so as we solve, we can do it step by step, but you end up with this. The entire right-hand side of the equation is 35,488.64. So that's the amount of elastic potential energy that he has when he has fully stretched the cord. Over here on the right, or sorry, on the left rather, we have 617.4 times h. Again, I'm trying to solve for h. I need it by itself. So I'm going to divide both sides by 617.4, leaving me with a height of 57.5 meters. So again, if you can write that equation and then substitute the things in, you can solve for that height. Are there questions about this example? Not yet. Okay. What about this? Okay, same scenario, but now we're going to look at point 1 and point 3. It says, if a 63 kilogram bungee jumper plunges from a height of 57.5 meters at point 1 before stretching the bungee cord and bouncing straight up to a new max height of 33.1 meters at point 3, if you watch this, he doesn't bounce all the way back up to where he started. He only bounces up about halfway-ish. Okay, how much energy is dissipated? We have to have dissipated energy. Okay, there's no way that you couldn't. If you didn't have that, he would bounce right back up to where he started and he would go forever up and down on that bungee cord. But when you stretch a bungee cord, it makes a lot of heat. If you stretch a rubber band, it gets hot. Same idea. Okay, so there is energy dissipated from the system due to that basically friction between the molecules that make up that elastic band. Okay, and so you get this heat generated and you don't have as much energy at the end. And that's what it wants us to find. So if we're going to compare those 2 points, I know at point 1 I have GPE, but at point 3 I also only have GPE. He's not moving there. That's his max height before he falls back down. The cord's not stretched there, so all he has is his height. Now, are those 2 going to be equal to each other? No. So I know that I need to include either work done by friction or dissipated energy. Because the question asked for dissipated energy, I'm going to include it that way. But you could do GPE plus work equals GPE. Or this. You'll get the same thing. Okay? And so we have his initial GPE at point 1 equals his final GPE at point 3 plus whatever the difference is. Okay? How much was lost, that dissipated energy? Again, I don't have energies. I have masses and heights. So we're going to do mgh equals mgh plus dE. That's dissipated energy. And then our numbers go in. 63 times 9.8 times 57.5 equals 63 times 9.8 times 33.1. Those aren't going to be the same, so I also want to include that dissipated energy. So the entire left-hand side, that initial GPE is 35,500.5. His GPE after he bounces back up to point 3 is only 20,435.94. So yes, I lost energy. How much? We subtract. Okay, again, you could solve this in steps. Figure out his GPE at the top, figure out his GPE at the bottom, and then compare and then subtract. Or if you write the equation is going to make you subtract to solve for it. You get 15,064.56 joules of dissipated energy. Again, the question could have asked, what is the work done by friction in that bungee cord, and you would have given me negative 15,064.56, but it'd be the same magnitude for your answer. Questions about this? Again, guys, this is the stuff people were having some trouble with. So if you're still confused, please make sure that you ask today. I want you guys to try this one on your own. Okay, I'm going to walk around the room in just a second and see what you guys write for your energy transfer equation. At least get it started. Write the equation out. Okay, so the scenario is a 0.8 kilogram toy car is released atop a ramp from rest at a height of 1.7 meters. At the end of the ramp, it has a velocity of 5.1 meters per second. What is the work done by friction? If you can set it up, you're halfway there. Okay, so I'm going to give you a moment to read this, to think about what energy forms are present, and to figure out how you would write an energy transfer equation to solve for this. Okay, and then I'm going to come around and see what you guys wrote. So if you don't have paper out, take out some paper to write this out, and then I'm going to come check and see how you're doing with it in just a moment. All right, so it looks like most of you did start it out right. You figured out that there was gravitational potential energy at the top of the ramp, and that's it. Some of you got stuck there, some of you included kinetic, but it was at rest. Okay, so initially it's just gravitational potential energy, and then you have kinetic energy at the end, and the question is the gravitational potential energy at the top equal to the kinetic energy at the end? And since you don't know if it is, the question kind of implies that it might not be, because it asks what's the work done by friction. Because of that, we're going to include friction in our equation. Okay, so that we could solve for it in the event that they're not equal. So this is how I wrote mine. Now some of you wrote GPE equals KE plus DE, and that's okay too. You could solve for dissipated energy. Just make sure you check your sign at the end, because if you're answering work done by friction, it needs to have a negative in front of it. Dissipated energy won't. Okay, so just double check and make sure your answer makes sense. But this is what your equation looks like, because and what I saw several of you do, you just wrote GPE equals KE. Maybe, we don't know. That's the question. Do they equal each other, or is there work done by friction? And what is that work done by friction? Okay, so I included my work here. We're going to substitute in our variables and then our numbers. So that's 0.8 times 9.8 times 1.7 plus the work done by friction equals 1/2 times 0.8 times that velocity, 5.1 squared. Okay, the entire left-hand side of that equation, my initial gravitational potential energy is 13.328. My final kinetic energy is 10.404. So if you solved it in steps and you're like, okay, GPE, what's that? KE, what's that? And then are they equal? Your answer is no, they're not. Okay, I very obviously lost some energy. I went from 13.3 to 10.4. Okay, so how much did I lose? That's the question. What's the work done by friction? And it's the difference between the two numbers. When I solve for that, I get negative 2.924 joules. If you set it up to solve for dissipated energy, you got positive 2.924 joules. You then need to remind yourself, work done by friction is negative. I lost energy. I need a negative sign. Okay, so check your sign at the end. But you can solve it either way, because you will get the same magnitude for your answer. You just need to check your sign at the end. When you're writing these equations, net work, if you're writing it as work and you're trying to solve for work, it always is on the left side of the equation. Okay, it's not on the right, it's on the left. Okay, so that might help you if you're setting it up, if you're solving for it that way. When we add dissipated energy in, we think of that as like a product. We put that on the right. Again, the sign will be different, but we're solving for something different. So just check it. Okay, but it looked like most of you are on the right track. Hopefully you were able to get to that answer. Okay, but I want to ask you one more question, because this is what we could do. Okay, I could ask you this on the test or on the quiz or whatever, on your assignment today as well. Okay, so this looks a little bit different. I would listen up. What if the question had said a 0.8 kilogram toy car is released atop a ramp from rest at a height of 1.7 meters. At the end of the ramp, it has a velocity of 5.1 meters per second. If the ramp is 1.3 meters long, what is the force of friction? I don't necessarily have to ask you for work first. Now I did, but I don't have to. I could just go straight to, hey, here's the length of the ramp, what's the force of friction? And if you're solving for force of friction, if it asks you to solve for a force, you're going to want to find the work first anyway, because work is force times displacement. Okay, so because we already found the work, all I'm going to do is I'm going to take that work and I'm going to set it equal to F times D. I know my work, I know the distance that it travels on the ramp, so my equation looks like this. Again, this can be tricky, but if it asks you for force of friction, that means you need to find the work done by friction. Okay, or you could even substitute the variables in for it, FD, into the equation. All right, so now I'm going to divide both sides by 1.3, and my force of friction is negative 2.25 newtons, and it better be negative, guys. Make sure it's a negative number when we're talking about friction. Questions about that last little step? Because I think you have some forces of friction in your assignment today. All right. Then for the rest of the period, you are working on the assignment 902.3 work energy theorem problem set. Again, it's due tomorrow, but you don't have class time tomorrow, so use your class time today wisely. Get as much of it done as you can, and anything you're not finished with by the end of the period, you can work on tonight or even tomorrow night. If you have missing assignments, make sure you're getting those taken care of, and if you're looking for additional practice, open up that unit summary. If you have questions as you're working today, let me know. And again, guys, you better have paper out. Have some paper out as you're working so that you can write out those equations so that you don't make some silly mistakes as you're working through those problems. Again, please let me know if you have any questions.